What if the universe doesn't follow the rules we see every day? Have you ever truly looked at your hand and wondered what it's made of? Or gazed at the stars and questioned the fundamental nature of the reality we inhabit? For centuries, we thought we had the answers. The universe, according to classical physics, the physics of Isaac Newton, was a grand, predictable machine, a cosmic clockwork where planets followed perfect orbits, and every cause had a clear, calculable effect. It was a world of certainty, of solid objects and straightforward rules. If you knew the position and momentum of every particle, you could, in theory, predict the entire future of the universe. This comforting deterministic view reigned supreme for over 200 years. But at the dawn of the 20th century, as scientists began to probe the very smallest scales of existence, this elegant picture began to crack, revealing a world far stranger and more wondrous than anyone had ever imagined. Welcome to the realm of quantum physics. This is not just an extension of the old rules. It is a completely new operating system for the universe. It is the science of the infinitesimally small, the world of atoms and the particles within them, electrons, protons, and the quarks and photons that make up everything we see, touch, and are. Down here, in this subatomic domain, the familiar logic of our everyday world dissolves into a dizzying dance of probability and potential. The solid, predictable billiard balls of classical physics are replaced by ghostly waves of possibility. This is a world where particles don't have a definite location until we look at them. A world where a single electron can exist in multiple places at once, a state of being known as superposition. It's a place where particles can be mysteriously linked across vast cosmic distances, their fates intertwined in a phenomenon Einstein famously called spooky action at a distance, what we now call quantum entanglement. It's a reality where energy isn't continuous, but comes in discrete packets, or quanta, the very idea that gave this field its name. This radical departure from classical intuition didn't just add a new chapter to the book of physics. It forced us to tear up the book and start again. It fundamentally reshaped our understanding of reality itself, challenging our core assumptions about cause and effect, the nature of observation, and the very boundary between the observer and the observed. The pioneers of this revolution, Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, were reluctant heroes, often as baffled by their own discoveries as the rest of the world. They had unlocked a Pandora's box of cosmic secrets, and the implications were staggering. But this isn't just a historical curiosity or an abstract intellectual exercise. The bizarre rules of the quantum world are the bedrock of our modern technological society. The laser in your Blu-ray player, the transistors that power your smartphone, the medical imaging of an MRI scan, all are direct results of our understanding of quantum mechanics. And today, we stand on the precipice of a second quantum revolution. Scientists are harnessing these strange principles to build technologies straight out of science fiction. Ultra-powerful quantum computers capable of solving problems impossible for any classical machine, unbreakable cryptographic codes to secure our information, and even the tantalizing prospect of quantum teleportation. In this series, we will embark on a journey into this incredible world. We will explore the foundational experiments that shattered the classical worldview, meet the brilliant minds who pieced together this new reality, and demystify the core concepts of superposition, entanglement, and wave-particle duality. From the birth of the quantum idea to the cutting-edge technologies of tomorrow, prepare to have your perception of the universe turned upside down. This is the story of quantum physics, the story of reality itself. Let's explore the quantum basics: atoms, subatomic particles, and Planck's constant. At the heart of quantum mechanics lies a profound and baffling question. Is light a wave, or is it a particle? For centuries, we thought we knew the answer. In the early 1800s, Thomas Young's famous double-slit experiment seemed to settle it. He shone light through two narrow slits and observed an interference pattern on a screen behind them, alternating bright and dark bands. This pattern is a classic signature of waves. Think of ripples in a pond spreading out from 2 points. Where the crests of the waves meet, they amplify, creating a bright band. Where a crest meets a trough, they cancel out, creating a dark band. Case closed, right? Light is a wave. But the quantum world had a shocking surprise. We now know that light is also composed of discrete packets of energy called photons, So what happens if we turn the light source down so low that we fire only one photon at a time? Common sense dictates that each photon, like a tiny bullet, must pass through either the left slit or the right slit. Over time, we should see just two bright bands on the screen, directly behind the slits. But that's not what happens. Incredibly, even when sent one by one, the photons gradually build up the exact same interference pattern as before. It's as if each individual photon somehow passes through both slits at once, interferes with itself, and then lands on the screen as a single localized particle. This is the essence of wave-particle duality. The photon travels as a wave of probability, exploring all possible paths simultaneously. The mystery deepens even further. If we place a detector at the slits to see which path the photon takes, the interference pattern vanishes completely. The very act of observation forces the photon to choose a path and behave like a simple particle. This duality isn't just for light. Electrons, atoms, and even large molecules have been shown to exhibit this strange behavior. It's a fundamental principle of reality, challenging our everyday intuition and forming the bedrock of the quantum revolution. Quantum superposition, Schrödinger's cat, objects existing in multiple states at once. Quantum entanglement, Einstein's spooky action at a distance. From the mind-bending theories we've explored, quantum mechanics has blossomed into a technological revolution that is actively shaping our present and defining our future. It's not just abstract mathematics and philosophical debate, it's the engine behind some of the most powerful tools humanity has ever conceived. Perhaps the most exciting frontier is quantum computing. Classical computers, like the one you're likely watching this on, think in bits, ones and zeros. It's a binary black and white world. But quantum computers operate on a completely different level. They use qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. And thanks to entanglement, the states of multiple qubits can be linked in a complex dance, no matter how far apart they are. By harnessing these properties, a quantum computer can explore a vast number of possibilities simultaneously. While a classical computer tries every key to a lock one by one, a quantum computer can essentially try them all at once. This incredible power won't replace your laptop, but it promises to solve problems currently impossible for any supercomputer, designing life-saving drugs by simulating molecules with perfect accuracy, creating novel materials with unimaginable properties, and optimizing complex global systems. We are at the dawn of this new computing age, and the possibilities are staggering. But with great power comes great risk. The very same power that allows a quantum computer to design new medicines could also be used to shatter the digital security that underpins our modern world. Most of our current encryption methods rely on mathematical problems that are too difficult for classical computers to solve. For a mature quantum computer, however, breaking this encryption would be trivial. This creates a quantum threat to our banking, communications, and national security. But quantum physics provides not only the poison, but also the antidote, quantum cryptography. The most promising method is quantum key distribution, or QKD. It works on a simple quantum rule. You can't measure something without disturbing it. The key is encoded onto individual photons. If a spy intercepts them, the act of measuring alters the photons, creating detectable errors. This immediately alerts the users to the breach. It's security guaranteed by the laws of physics. While quantum computing feels futuristic, you are already living in a world built by quantum mechanics. Every time you use your smartphone or computer, you are using technology that would be impossible without it. The heart of all modern electronics is the semiconductor, and its behavior is purely quantum. Inside a silicon chip are billions of tiny switches called transistors. Our ability to control the flow of electrons through these transistors depends on understanding quantum concepts like energy bands and quantum tunneling. It was by mastering the quantum behavior of electrons and materials that we learned to create these microscopic switches, paving the way for the entire digital age. And what about the laser? From barcode scanners to the fiber optic cables that carry the internet, lasers are everywhere. The word laser is an acronym for light amplification by stimulated emission of radiation. That stimulated emission is a quantum process. In simple terms, atoms are pumped to a high energy state. One atom releases a photon, which stimulates other excited atoms to release a cascade of identical photons. This creates the perfectly coherent, focused beam of light we know as a laser. Beyond these incredible technologies, the The quantum revolution has forced us to confront the deepest questions about the nature of reality itself. For centuries, classical physics gave us a comforting vision of a clockwork universe, a deterministic cosmos where, if you knew the position and momentum of every particle, you could predict the future with absolute certainty. Quantum mechanics shattered this deterministic dream. At the fundamental level, the universe isn't a clock, it's a casino. The wave function doesn't tell us what a particle is doing, but rather the probabilities of what it might be found doing upon measurement. This inherent randomness deeply troubled physicists like Einstein, who famously declared, "God does not play dice with the universe." Yet experiment after experiment has confirmed this probabilistic nature is a core feature of our reality. This leads to an even stranger question. What is reality when we're not looking at it? Does a particle even have a definite position before we measure it? The Copenhagen interpretation suggests properties like position are undefined until measurement forces an outcome. In a sense, the observer helps create the reality they observe. Other interpretations offer even more radical alternatives. The many worlds interpretation proposes that the universe never chooses at all. Instead, every possible outcome of a quantum measurement occurs, each in its own separate, parallel universe. Every time a quantum event happens, the universe branches. In one universe, the particle was found here. In another, it was found there. In this view, there is a near infinite tapestry of parallel realities, and we are simply experiencing one path through it. From the transistors in our pockets, to the philosophical debates about parallel worlds, quantum physics has completely rewritten our understanding of the universe. It took us from a predictable clockwork cosmos to a strange, probabilistic reality woven from uncertainty and potentiality, and the journey is far from over. The greatest challenge in physics today is to unite quantum mechanics with general relativity to create a theory of everything. What will such a theory reveal? Will it explain the mysteries of dark matter and dark energy? Will it tell us what happens in a black hole, or what the universe was like at the Big Bang? Could it even shed light on the nature of consciousness itself? 100 years ago, we had no idea the quantum world even existed. Now, we are harnessing its power and grappling with its profound implications. If the first quantum revolution rewrote the rules of reality, we can only wonder what the next one will reveal. The universe is stranger and more mysterious than we ever imagined, and the quest to understand it is the greatest adventure of all. The quantum realm is the ultimate frontier, a place of deep mystery and infinite possibility. If you're as fascinated by these questions as we are, and you want to continue exploring the cutting edge of science and the fundamental nature of reality, then join our community of curious minds. Subscribe to Physics AI for more deep explorations into the cosmos and our quantum world. Thank you for watching.